In this module, you will learn about the pH of acidic buffers. Let's first learn about what a buffer solution is with the help of a simple experiment. For the experiment, you'll need 4 250 ml beakers. Label the beakers A, B, C and D. Take about 100 ml of distilled water in beakers A and B. Take 100 ml of a mixture of acetic acid and sodium acetate in beakers C and D. Now, find the pH of the contents of all the 4 beakers. Next, add a few drops of hydrochloric acid to beakers A and C and a few drops of sodium hydroxide to beakers B and D. Once again, find the pH of the contents of all the 4 beakers. The contents of beakers A and B show a variation in pH when an acid and a base are added. On the other hand, the contents of beakers C and D do not show any variation in pH when an acid or a base are added. Therefore, we can say that there exist some solutions that resist any change in pH when small amounts of acid or base are added to it. Such solutions are called buffer solutions. Generally, a buffer solution can be prepared by mixing either a weak acid and its salt or a weak base and its salt. Based on its pH value, a buffer can be classified as acidic buffer or basic buffer. An acidic buffer is a buffer whose pH is less than 7. A common example of an acidic buffer is a mixture of acetic acid and sodium acetate. Another example of an acidic buffer is a mixture of formic acid and sodium formate. A basic buffer is a buffer whose pH is greater than 7. A common example of a basic buffer is a mixture of ammonium hydroxide and ammonium chloride. Another example of a basic buffer is a mixture of ammonium hydroxide and ammonium nitrate. With the help of an example, let's now try to understand how the pH value of an acidic buffer is calculated. Take a mixture of acetic acid and sodium acetate in a beaker. Acetic acid is a weak acid, so it dissociates very slightly. On the other hand, sodium acetate is a salt of a weak acid and a strong base, and therefore it dissociates completely. Hence, the mixture now contains acetic acid molecules, acetate ions and sodium ions. Here there exists an equilibrium between acetic acid molecules, acetate ions and hydrogen ions. Now, the acid dissociation constant Ka is equal to concentration of H plus ions multiplied by concentration of acetate ions divided by concentration of acetic acid. After rearranging, concentration of H plus ions is equal to Ka multiplied by concentration of acetic acid divided by the concentration of acetate ions. Now, taking the negative logarithm on both the sides of the equation, we get minus log of concentration of H plus ions is equal to minus log of Ka minus log of concentration of acetic acid divided by concentration of acetate ions. You know that minus log of hydrogen ions is equal to pH and minus log of Ka is equal to pKa. Therefore, we can now write the equation as pH is equal to pKa minus log of concentration of acetic acid by concentration of acetate ions. We can also write this equation as pH is equal to pKa plus log of concentration of acetate ions divided by concentration of acetic acid. Here, the concentration of acetate ion is almost equal to the concentration of sodium acetate, as sodium acetate ionizes completely to form acetate ion and sodium ion. Hence, pH is equal to pKa plus log of concentration of sodium acetate divided by concentration of acetic acid. We can generalize this equation as pH is equal to pKa plus log of concentration of salt divided by concentration of acid. This equation is called the Henderson-Hasselbalch equation. According to this equation, the pH of an acidic buffer consisting of a mixture of a weak acid and its salt depends on the pKa value of the acid, the concentration of the salt, and the concentration of the acid in the solution. If the concentration of the salt is equal to the concentration of the acid, then in such a case, pH is equal to pKa. Let's now study the buffer action of an acidic buffer consisting of a mixture of acetic acid and sodium acetate. Add a few drops of hydrochloric acid to this mixture. Since hydrochloric acid is a strong acid, it will dissociate completely to release hydrogen ions into the mixture. The hydrogen ions will then combine with the acetate ions to form weakly ionized acetic acid. Since the newly introduced hydrogen ions are neutralized by the acetate ions, there will be no change in the pH of the mixture. Similarly, if you add a few drops of sodium hydroxide solution to the mixture, sodium hydroxide, being a strong base, will dissociate completely into sodium ions and hydroxide ions. The newly introduced hydroxide ions get neutralized by the acetic acid molecules. So, once again, there will be no change in pH of the mixture. You have now reached the end of this module. In this module, you learned that buffers resist any change in their pH sought to be brought about by the addition of an acid or a base. The pH of acidic buffers is less than 7, whereas the pH of basic buffers is greater than 7. The pH of an acidic buffer containing a mixture of a weak acid and its salt is equal to pKa plus log of concentration of salt divided by concentration of acid. The acetate ions in a mixture consisting of acetic acid and sodium acetate buffer neutralizes the incoming of hydrogen ions that are produced when hydrochloric acid is added to the mixture. The acetic acid present in a mixture of acetic acid and sodium acetate buffer neutralizes the incoming hydroxide ions that are produced when sodium hydroxide is added to the mixture.